Yeah, hello everybody. Today we will dive in, yeah, deeply into the neoclassical trade theory. We started with the Ricardo model, linear production functions, only one production factor, mainly labor, and then we went further and we introduced two production factors, capital and labor, where we said that one of these factors should be specific, and we argued that quite often we find this. But anyway, um, in order to create a general model, we also have to think of flexibilizing the specific factor. Compare this, for example, with your argumentation when you are looking at cost functions and you are describing costs, differentiating between fixed costs and variable costs. And then in the long run, you argue, well, in the long run, there are no fixed costs because you can sell your machinery and buying some other capital which you can use then. And more or less the same argumentation we have here, that in the long run, we should look at the situation when all factors are flexibilized. But on the other hand, everything else will be more or less the same, but we are then also introducing some assumptions about the two countries which will trade with each other, because of course, in order that you can get something out, they cannot differ that much from each other. So what we will do then is to go into the so-called Heckscher-Ohlin. Heckscher and Ohlin, both two Swedish economists, and so in the beginning of the 20th century, they developed their international trade model, where we introducing two goods, A and B, two factors, capital and labor, and still, of course, two countries, one and two. And here are now the assumptions which we are doing about production is now that we have two different goods. They are produced, of course, differently, but we assume that the production technologies within the countries producing A and B do not differ. So this is a difference compared to Ricardo, because there, of course, we assumed different production functions due to the slope of their transformation curve. In this case, the difference between the countries we introduce at another point. So, in general, again, we have neoclassical production functions, means positive but decreasing marginal products. And now this would be a really crucial assumption within this model, this constant returns to scale production. Remember, in the other two models, there, of course, we also assumed these constant returns to scales, but especially in the specific factor models, we didn't use for the argumentation the constant returns to scale production functions, but in the background, still, these constant returns to scale means zero profits in optimum. And this is, of course, in line with fully competitive markets. And now, and this I will show again in a minute, but please remember your micro course. I recommended that you should have a look during the last week in your micro slides, that if we have a production technology which exhibits constant returns to scale, that then the cost minimizing combination of input factors producing these goods will be constant if the factor input prices are also given, or the ratio of these factor input prices are given. So if we assume that the wage rate is given and the interest rate or the ratio of these two factor input prices are given, then together with constant returns to scale, we know that the input combination of our factor inputs, capital and labor, will be in optimum always the same ratio. And therefore, it is enough that we now assume the difference between the production of these two products, that we just assume the ratio of capital over labor is just different between these two products. So one product is then produced capital intensive, and this just means that the ratio of the two inputs is larger than the other one. And in our case, of course, without loss of generality, we just assume that in our case, product A will be the capital intensive, and then of course vice versa. Compare here this with the Ricardo model. This means that product B is produced labor intensive. So, and now we assume, as we have assumed in the specific factor models for labor, for the non-specific factor, that factors are fully mobile between sectors. Now, between sector A and B, we can just interchange labor and capital as we wanted. But what we assume is that we cannot internationally exchange factors. So we cannot exchange capital and labor between the two countries. Well, this is an, of course, strict assumption, but in general, look, for example, for labor, then it is a quite good assumption that we say it is not that easy that you just start to work in another country. Within the European Union, well, there it is not the case, but if you want to work outside the European Union, then there are many borders that you really can work there. For example, if you want to work in Switzerland, then always the firm in Switzerland has to argue that there is no Swiss guy which can do the work as good as you can do it. And now here, this is the difference between countries. How do they differ? The countries should only differ in their overall ratios of the factor inputs. So one country should have, and again, it is crucial that we do not argue in absolute terms, but only in relative terms, as we have done it also in the Ricardo model when we were talking about comparative advantage. Here now we assume that the ratio of overall capital divided by labor is in one country larger than in the other. So if K bar 1 over L bar over L bar 1 is larger than K bar 2 over L bar 2, then we call this country capital abundant, and the other one, just taking L over K, this of course then means that the other country is labor abundant, and that we just choose the first country to be capital abundant, this is of course also without loss of generality. We just can choose one. The argumentation would be only in opposite if we would choose the other country. Okay, then see here, neoclassical production functions with constant returns to scale. Of course, we assume perfectly competitive goods and factor markets. And also, we make now an assumptions about the preferences in the two countries. And these two countries should also do not differ in their preferences. So from there we derive more or less the demand for our goods A and B, and these preferences should be also homothetic. Have you talked about homothetic preferences in micro? What is meant by this? Well, this means that utility is a function with homogeneity of degree 1, of course, or a monotonic transformation. Homogeneity of degree 1. Hopefully you have talked about this mathematical property not only in micro but also in other lectures. Well, I talked in macroeconomics about it. Homogeneity is in the end the same as constant returns to scale. So this just means u of x1, x2 times some factor lambda is the same if we just would multiply both inputs, here our consumption goods x1 and x2 with a factor lambda, u of lambda x1 lambda x2. So this is the same as here the constant returns to scale, lambda f of kl equals just doubling our inputs, multiplying both inputs with the same factor lambda. Well, why do we make this assumption? Well, in general, we have talked about preferences, and preferences are purely individual. You can always say anything when you are comparing some consumption baskets. But here, this then means, of course, mathematically, then the same as here, as I argued in the production, that in optimum, the relation of our factor inputs is constant, and this means given the prices or given the price ratio, also our relative demand for the two goods is constant. This then, of course, means if we are doubling all prices from all goods, that this won't change our basket because we are relying only on relative prices. And this is, of course, I think, not a very restrictive assumption. Think of here we are in the lecture of international trade. For you, it should be more or less no. It shouldn't be. It shouldn't have any impact if you would pay your goods in euro or in British pounds, and then you have also just to multiply the prices with the exchange rate. Okay, and these are all our assumptions, and with these assumptions, now we want to go into our model. At first, we are deriving, as we have done it in the other models, the situation under autarky. This is then more or less only just a general equilibrium analysis, and because of that I recommended that you have just a look into your micro slides because this is just a repetition of what from these things you have done in microeconomics. Okay, so minimization. Oh. So about this, I have already talked qualitatively. Today, I will mainly go through the analysis via diagrams. You hopefully already know from your studies, and then on Thursday or next Tuesday, we will do also the math for this model. Okay, so let's start. Cost minimization. So we have just, let's take our, or let me write it down it here, our production of good A of capital and labor. This is our amount of A, and we had our costs, and these costs are just C of K and L is wages times labor plus interest rate times capital. Oops. Here's one. And then you set minimizing costs subject to A, the amount of output is just given. So we just say we want to produce 3 units of our good. How do I have to produce? How much capital? How much labor do I have to use given my two prices that my costs will be minimized? And this you have done graphically, that in this case you just argued, well, if this is a fixed number that you then obtain similar to the indifference curve for the utility maximization, that you now argued, okay, due to our assumptions, positive but decreasing marginal products, that you obtain these convex isoquants, representing all possible factor input combinations in order to produce, for example, 3 goods of A. So from this, you got your isoquants. So this would be then some isoquant for good A. And then, and since I have it here, oops, einfügen. Then we argued the cost function is just a linear line. And this linear line, since we want to minimize these costs, that we just move this linear line as far as possible downward here to the left. And that the cost minimizing point we just obtain then similar to utility maximizing, where the slope of our isoquant meets the slope of our cost function. So that this is then our optimal or our cost minimizing point for producing A. And then, due to constant returns to scale, we know that if our overall costs are reduced, so a parallel shift of our costs, that then and this I have written down at the former slide, we obtain just the same factor input ratio. So that for this we would have here at the same factor input ratio the cost minimizing point for good A. So this linear line, oops, where do we have it? Would be then this cost minimizing factor input ratio of good A. Well, this of course then we can do the same thinking for good B. And now remember, for good B we have assumed that the cost minimizing input ratio of good B is below the cost input ratio of not the cost, the factor input ratio of good A. So if I now want to draw the factor input ratio for good B, how do I have then to draw this line? This should be now a red line for our good B. Where do I find it? In this diagram. How can I draw it? So the slope of this blue line is representing the factor input ratio cost minimizing for good A. I know that it is also a line for good B, and I know that the input ratio is lower than this of good A. How do I have now to draw this line? And I will use this one here. How has it to look like? So the slope of this blue line is representing K over L for A. How do I have to put this red line if this should represent a lower ratio of K over L? It's still K over L, but a lower ratio. Yes, just a flatter line. Of course, we are producing nothing when when we have no factor inputs. So it would look like this, and then the isoquants for good B would then be situated here at these points tangent to our cost functions. So this would be then K over L of B. So this is from cost minimization. And now we can deduce from this diagram, well, I just wanted to do it like this here. Oops. A relation of factor intensities and factor price ratio. So on the vertical line, we put our factor price ratio, wages over interest, and on the horizontal line, our capital over labor. So then, if we assume just one given factor price ratio, W over R prime, this is just one number. Then, given this factor price ratio, let's say this would be then the coinciding capital over labor ratio for good A. Also some number. Somewhere it has to be. We didn't have directly specified how our production function is. It could be a SES function, it could be Cobb-Douglas anyway, only constant returns to scale. So this would be. But now, from this cost minimizing diagram, we can deduce relatively to this point, where do we find now the coinciding capital over labor ratio for good B? Coinciding the same factor price input ratio. So it has to be somewhere on the horizontal line, but is it to the left or is it to the right? To the left, because here the slope is lower, so it has to be maybe somewhere here. B prime. And then we can ask ourselves, when we are rising wages, we W over R double prime. Well, sometimes it's easier. Well, how does this ratio rise? Well, if you take, for example, interest rate constant and just doubling wages. So labor becomes relatively more expensive. What will this mean in general for your production? How will you shift the production input factors if one input factor will be more expensive? To the, yes. So you are taking from the now more expensive factor, you're reducing this one, and you are increasing the other one. And if we take this ratio here, and if we assume that the wages are increasing, what does it mean then for the new optimal ratio of capital over labor? Is it increasing or decreasing? Labor becomes more expensive. It is increasing because we are shifting from labor to capital, because capital is now relatively less expensive. Okay, so we obtain for both goods A and B, because the argumentation is for both goods the same. We obtain for both some increasing function, maybe here, and well, let's go a little bit more to the left. Then I can draw this easier. Let's say here and here. So we obtain these two dependencies of A and B in this relative factor price versus relative factor intensities. Sorry, the other way around. This was wrong. This is good A, and this is good B. And remember, this was capital intensive produced, and this was labor intensively produced. Okay. Then, well, maybe can draw it the next time a little bit larger. Let's go. We keep this dependence in mind. This we need later on. Now, let's go to, again, our cost minimization and the so-called Edgeworth box. Have you heard about this concept of Edgeworth already? Maybe in microeconomics? This is a British economist. So again, then I will take my cost minimization part here. And we use this one. Well, actually, I have enough space, so then let's do it here. This, so, okay, because we want to know, since we have the resource constraint that LA, now let's say we are in country 1, LA bar, no, LA plus LB is L1 bar, the total labor amount we have in country 1, and KA, well then we have to take here also an index. I will skip these indices in a minute in the next diagram, because the argumentation is of course then the same for the other country. K1 bar. So how do we divide both factors between A and B? So what would be the optimal choice for the division of both factors? And remember, this we have also done in the specific factors models, where we said, well, we have two labor demands, and the intersection of these two labor demands, this is the division with which one I'm producing in the agricultural sector and with which one I'm producing in the industrial sector. Right now, we are not arguing via the overall demand, but what would be under, oops, this is not good. This is now doubling. I thought let's do it like this. No. What was the shortcut? This one. No. Yeah. Up. And let's put it but in a Word document. And then I can move backward. No. This doesn't function. Anyway. Mm, but this is this we don't need. This one we don't need. This not. And the rest can be seen, I think. I have to be a little bit more careful when I'm copying things. A and B. Sorry for this. Okay. Yeah. How should we, assuming parallel cost minimization of A and B simultaneously, how do we would in the optimal case divide both goods, both factor inputs producing both goods? And for this, I will take these two. We can draw these so-called Edgeworth box. So, and what we are doing here is we are looking simultaneously on both goods. On the left one, we just draw our known diagram for good A. For this good A, we know that we have just an isoquant IA prime given at again just one production of our good A, let's say 3 units, K and L again. And now we can argue, since we have our resource restrictions, that in the end, the total amount of L which we can use is just our L bar. Nothing more is possible. But if we, for example, use that much of L for producing L, then the rest one we can use for B. So then this would mean this would be the origin for our product B. If we are here and here, so using the total factor amount K bar and L bar for the production of A, then this means there is nothing left for B. So we are then just in the origin of product B. So and then you just take your view around looking now from the upper right. And this then would mean if we draw now the same picture, an isoquant for product B, then we could say, okay, given some amount let's say 5 units of B, this would be then here an isoquant for B. And now we can ask ourselves, what would be an optimal combination using all resources in our economy? Then optimal Pareto efficient basket of production of A and B. Pareto efficient, you have already talked about this concept. So, laxly spoken, we can say we don't want any resources. And since we have assumed positive marginal products, this is the same assumption as you have made it in utility theory when you have made the assumption more is always better. So we know that in optimum we will use 100% of our factor inputs of L bar and K bar. So to speak, no wasting of resources. So then we could say, well, then maximize production of A given a fixed amount of B, or formally max F A of K and L subject to B is some fixed amount, maybe this one here given by this isoquant in this graphic. Then I should also write here better not B bar but this B prime. And we have another resource or two other resource constraints and also subject to L A plus LB equals L bar and subject to KA plus KB equals K bar. Well, of course, this we can do taking these Lagrangian formalism, but if we look at this graphical situation, this maybe is just our starting point. And now we are fixing the amount of B. IB prime should maybe 4 units of B. How would we now change this situation here, given as a starting point, in order to maximize the output of A? This is some possible output of A. What could be a better or a larger one? Where would we then find the isoquant of another production level of A, which is feasible, which we can do if we do not alter the isoquant of B? Where could it be situated? For this, you have to remember an isoquant. If you move it to the upper right, is it then representing more or less production output of our good. It would be more if we go to the upper right. So if we fix the amount of B represented by this isoquant I have drawn for B, then this would mean, well, still I can move outward with this restriction the isoquant of A as far as possible. And as far as possible means, well, the most outward lying isoquant which would be possible. And again, as we had it here, where we have the restriction by a linear line, now it's just our isoquant which is the restriction. So in this case, given B prime, our optimal isoquant for A would be again just tangent to the isoquant of B. Prime just having this situation. So this would be then this Pareto efficient output combination that I do not waste any resources. But of course, let's take here another color. We could have also such a situation. Again, I A double prime and B A I B double prime. And now let's say we look at this problem the other way around. Just interchange A and B, and now we want to maximize, given the green situation, we want to maximize the output of B given the output of A represented by I A double prime. What would we do then graphically? Yeah, outward. What do you mean by outward? Shifting B outward to the left or to the right? To the left. Okay. So you are just have just the perspective from the other origin from B, and so of course, yeah. Then it's of course an outward shift. You are totally right. So to the downward left, we would move then this one, and maybe we obtain here another Pareto efficient output. So this is Pareto efficient output level, and this one is another possible Pareto efficient output level. And now we make the thought experiment. This we have to do for all possible situations. So in the end, we are looking for all possible points in this graphical representation where the isoquants of A and B are tangent. So maybe here would be one, or downward here, or upward here. And then we obtain the so-called contract curve. The contract curve represents all possible output combinations which are Pareto efficient. contract curve represents all Pareto efficient output combinations of A and B. Well, and it can be shown that if we have these positive but decreasing marginal products, that then in this representation, this has to be a monotonically increasing function. So, and remember what we have used quite often is, how do I have it? Here, the blue one, this was the transformation curve of the specific factors model. Or in the Ricardo model, B and A, we had our linear lines as our transformation curves. And what we now want to deduce is the transformation curve within the specific factors model. Because what we have derived now are all efficient output combinations of A and B. And these output combinations now we want to represent in a diagram with A and B on the axis. So now I will take this one. Oops. And let's go until here. Oh, I didn't got anything, everything. Then I have to redraw it. So, L and K, B, A, and our contract curve. And these are all output combinations. So this would represent A1, B1, A2, B2, A3, B3. And this we can then put in a diagram where we now want to move this combination here. Well, we don't know how definitely looks like our production function, but if we are at this production point here, we could assume, since at this point here we are using almost all resources for the production of B. This is AL1 and this is KA1. So we can then suppose that we are producing quite a lot of B and not that much of A. So that maybe this one represents then a production point like here. This one is maybe a production point like here. And this one maybe here. This we have again to do for all our points on the contract curve, and in the end, very surprisingly, we also end up with a transformation curve which is looking like this. Well, In general, we can only derive that such a transformation curve should be in A and B a monotonically falling function, but if we assume constant returns to scale, then we can definitely show that it should have also this concave shape. So transformation curve for A and B monotonically falling. This follows from positive but decreasing marginal products and concave. This follows from constant returns to scale. So let me take this one then also on the other slide. That you are then not puzzled that I skipped this slide here. Oops. Nope. Why is it not? So, okay. And now we are almost done. I have some time left because now we can argue in the same way as we have already argued in the specific factors model. Now we can say, okay, I have my transformation curve looking like this. This comes from our Edgeworth box. B, A, K, and L. And now assume fully competitive markets a given output price ratio PA over PB. What have we done in the Ricardo model and in the specific factors model? There we had our income line. So our income line was E equals PA times A plus PB represented by this linear equation. And then remember in the end of the argumentation in the specific factor model, we just said our transformation curve this represents our production possibility. Given our production possibility, we want to maximize our income. So our optimization problem now, having derived all this, would be max E of A and B subject to our given transformation curve. So again, our aim is now this linear line. This we want to maximize. So we want to move it as far as possible outward to the left, to the right, sorry. So again, we obtain the optimal production point where the slope of the income line equals the slope of our transformation curve. This is absolutely the same argumentation which we have made already. This means slope of transformation curve equals slope of income line, and this is just our price ratio. So this means this would be our optimal production point where we have some given, let's also always say this would be some PA over PB prime. So, but now we can, so to speak, move backward in our argumentation. This is our optimal production point given some price ratio. How do we produce this? Well, maybe this point represents in our Edgeworth box this point on the contract curve. In the contract curve, we knew that both isoquants have to have the same slope, but what else have to be there the same? We had also, let's say this is now only K and L. Oops. That this means also that the slope of our isoquant has to coincide the slope of our cost line. And there the slope was some ratio of our input prices of our factors. So this means then, together with these two, that the price ratio of A and B, then PA, PB prime pins down also our factor price ratio W over R. Have you got this argumentation? We obtained the transformation curve from cost minimization, then via the Edgeworth box, that all these slopes has to coincide. And now by our income maximization, we obtain some special point on the transformation curve. This transformation curve represents in our Edgeworth box a point where both slopes of the isoquants have to coincide. And from cost minimization, these slopes have to also coincide with a specific factor price ratio W over R. And now the last one, from this to this, we also have argued that this cost minimization also gives us a specific capital over labor ratio. So in the end, and then I think I got it here. There we had on the first slide K over L, that this one also pins down our capital over labor ratio. And W over R prime pins down also our capital over labor ratio of A and B. A, our factor input ratio, this I should also write down. Factor input ratio, and of course also for B. This we have to use also later on. And what we can derive from this now also is our relative supply that we, so to speak, obtain a dependence between our price ratio AB and our output ratio capital A and B. So this is the output ratio. Because given our PA PB prime, this is maybe somewhere here. This represents A star over B star. I should also not take star, but prime, sorry. If I take the ratio of this, this could be maybe here, A over B star. So this would be some point. And then, of course, I'm also interested for the dependence of another ratio. So let's do this again in another color, green. Assume A is PA, sorry. PA is increasing. What changes in the first diagram in the upper left? Everything else is still the same. Which curve is changing? In this diagram here. If just the price of good A is doubling. Income line, yes. And how does it change? So A enters the slope, will be the slope larger or smaller, so will our income line be flatter or steeper? Steeper if A is increasing. So since I know that I have this concave transformation curve, this means that our now optimal point has also to move downward right on our transformation curve. Because now, maybe here, this would be now our larger a ratio of PA over PB. Let's say this then double prime. This means that PA over PB double prime larger than PA over PB prime. Well, this means I obtain now a new optimal production basket of A and B. A is increasing, B is decreasing. Of course, what happens then to our ratio A over B relative to A over B prime? If A is going up and B is going down, then A over B relatively to the starting point moves to the right. It has to be, let's say, A doubles and B 30% down, then of course I obtain a larger number. So maybe it would be here, A and B double prime. And our price ratio, well, this was our assumption that it is B larger. So PA over PB double prime would be maybe somewhere here. So in the end, doing this for all possible price ratios, again, we make this general thought experiment. Very surprisingly, we obtain something like a supply curve depending for our relative output depending on the relative prices. So this would be then supply curve, not A, sorry, supply curve for of A over P depending on the price ratio. Okay, so, and this total analysis, now we have, so to speak, do simultaneously for our both countries. Also, this I forgot one thing here, and this we can also take in our diagrams additionally. We can in general derive demand from our preferences. Well, given our price ratio, This is now definitely what you have learned in microeconomics. The household optimization, this was your budget line, the slope of your budget line was represented by the price ratio as we have it also here. Let's also say that this is P over B, PA over B, PB prime. And we had our indifference curve, I prime with the household optimum here. And from this, we then can say, well, in the optimum, given the price ratio have to coincide the slope of our transformation curve and simultaneously also have to coincide from our standard household optimization also the slope of the indifference curve of our indifference curve. Well, and with standard assumptions from this, we of course then obtain also normal goods A over B, PA over PB, a falling demand curve. This you have done in your microcursor. So this would be our demand curve. So in general, we can then introduce this demand curve also here. This is demand. Oh, I should have, since I have here already A over B prime, then the, I think this now I can do here. Then it should cut, of course, in this point. So what we have done here is, so to speak, the general equilibrium of one country. And the next step on Thursday will then to look simultaneously at the two countries and then asking what happens if they are opening their borders and introducing trade. Okay, thank you very much for today. I write it down here. So this is the autarky equilibrium.